Swayam Prabha. Digital India. Educated India.
Welcome everyone. So after this is the third tutorial lesson, and after compaction, so we are going to start today with the permeability. Now I am going to discuss today a few problems on permeability, and the first problem says that drainage pipe becomes completely blocked during a storm by a plug of sand followed by another plug of a mixture of clays, silts and sands, 0.5 meter long. When the storm was over, the water level above ground was 1 meter. Now a figure for this is given here. So this is the water level and this is the brick wall. So this height is 1 meter as said in the question, and there is a down pipe connected. This is the layer of sand. This height is given as 2 meter, and this is the clay soil, while this height from the middle is said to be 0.3 meter. Now this is the drain pipe. This point is A, this is C, and this is the B, and the datum is here. This is the clogged mixture of silts, sands and clays. So this is the plug of this point is the plug of sand, while this is the plug of clay, silts and sands, and this is 0.5 meter long, and this entire length is 1.5 meter. This is the brick wall. So it is asked in the question to first plot the variation of pressure elevation and total head. Over the length of the pipe. Now, the first strategy that we are going to accomplish during this problem is that we have to select a datum. Now, so basically we are going to first select a datum. Now, as we have said in the question that the datum is selected at this point at the bottom B, at the bottom of B. So, basically this point is selected as the datum. Now, we have selected the datum. Now, from the information given, we have to calculate the total head at the points A and B, and the difference in the head is head loss over both the plugs. But we have to calculate the head loss due to sand first, and second head loss due to mixture of sand, clays and silts. Now, the continuity equation, as we know, will provide the opportunity to find out the head loss over the entire pipe. Now, let us see how to find out the head loss over the entire pipe length. So, first we have selected a datum. Now, basically we determine the head loss at point A. So, you already know that point A is the point where basically the sand is plugged. So, from this point we can say that the head loss means the first is the HP, the pressure head loss at the point A is equivalent to 0.3, because this height is 0.3 plus 2 is this point, 2 is this length plus 1 meter. So, this is equivalent to 3.3 meter. So, basically the total head loss at the point A, and the velocity head loss is, the velocity head is 0. So, because water flows very slowly through soils, as I have said previously, as we have already covered in the lecture section, that water flows very slowly. So, always the velocity head loss is 0, only there is a datum head and there is a pressure head. So, we have found out what is the datum head and the pressure head is, and this is equivalent to 3.3 meter. Now, similarly the head loss at the point B will be equivalent to 0 meter, because as you can see that it lies on the datum. So, basically it is neither above the, it is neither there is a pressure head nor there is a datum head. So, both of them is actually equivalent to 0 in this case. Now, the head loss in each plug has to be determined. So, head loss in plug. Now, first we have to find out what is the head loss in between A and B. So, this is HA minus HB mod of that is equivalent to 3.3 meter. Now, let us consider that delta H1 is the head loss, L1 is the length, K1 is the coefficient of permeability. Now, if that is the case, then and delta H2 with the head loss, L2 with the length and K2 with the permeability. Now, we are going to refer the first clogging as clog 1, this is due to sand entirely, and this as clog 2, this is due to mixture of silts, sands and clays. So, and Q1 and Q2 I am not writing here, but Q1 and Q2 are basically the quantity of water per unit area through the clog 1 and clog 2 respectively. So, let us start with Q1, that is the quantity of water that is passing through clog 1. Now, this is equivalent to A into K1 into I1, because from Darcy's law we get that Q is equal to K into I into A, where K is the coefficient of permeability of material, I is the hydraulic gradient, which is equivalent to H by L, where H is the head loss over the length L, and A is the area of cross section of the material. So, here similarly for clog 1 we get Q1 is equal to A K1 into I1. Now, A is considered to be A because the area of the cross section of the pipe, as you can see, is almost same in both the cases. So, basically that is why we considered a single area A. Now, A into K1 into I1 will be equivalent to H1 by L1, or here it will be equivalent to delta H1 by L1, where delta H1 is the head loss over the length L1. So, this will be equivalent to A into, and for Q2 it will be equivalent to A into K2 into delta H2 by L2. Now, let us go back to the question and see that basically it is also given that the coefficient of permeability of sand is twice of the mixture of sands, silts and clays. So, in other words, K1 is equivalent to 2 times of K2. So, from here we get that Q1 is actually equivalent to A into 2 K2 into delta H1 by L1. So, this is equivalent to 2 A K2 into delta H1 by L1, while Q2 is equivalent to A into K2 into delta H2 by L2. Now, as we have said in the beginning that basically in the variation of pressure, when we will discuss about this head loss due to a mixture of sand, silts and clays and the head loss due to the sand, we will connect both these two by the continuity equation. So, basically now we will refer to the continuity equation here. So, from the continuity equation, the flow must be same throughout the entire length of the pipe. So, that means basically Q1 must be equivalent to Q2. If this is the case, then we get that 2 into A into K2 into delta H1 by L1 is equivalent to A into K2 into delta H2 by L2. So, delta H1 by delta H2 is actually equivalent to A into K2 by 2 A into K2 into L1 by L2. So, this is equivalent to half into L1 by L2 or L1 by 2 L2. Now, what is the length of L1 and L2? Now, let us refer back to the figure. We will see that the length of L1 is 1.5 meter, while the length of L2 is actually 0.5 meter. So, L1 is 1.5 meter because L1 is due to the sand, while L2 is the mixture of sand, silts and clays. So, 2 into 0.5. So, this comes out to be 1.5. L1 is this length, that is due to the mixture of sand, while L2 is due to the mixture of sand, silts and clays, this mixture, while N1 is the mixture of sand. So, basically it is 1.5 meter. Now, we also know that the entire head loss is equivalent to 3.3 meter from A to B. As we found out previously that the entire head loss is equivalent to 3.3 meter, the head loss at B is 0 meter. So, the entire head loss is 3.3 meter. Now, we know that the ratio of the head losses is equivalent to 1.5. So, from here we get that delta H1 plus delta H2 is equivalent to 3.3 meter and delta H1 by delta H2 is equivalent to 1.5. So, solving this 2, we get delta H1 is actually equivalent to 1.98 meter, while delta H2 is equivalent to 1.32 meter. Now, we have to find out the head loss at the point. We have found out what is delta H1, what is delta H2. Now, we have to find out what is the head loss at the point C, that is the final head loss, because we have already known that the head loss at the point A is 3.3 meter, the head loss at the point B is 0 meter, and now we have to find out what is the head loss at the point C. So, this is the where is the point C? First, let us see, the C is at the junction of the two plugs. So, basically head loss at junction of two plugs is, that is at C, it will be equivalent to HC, that is equal to HA, because it is the head loss at the point A minus the head loss that is observed across this entire length of the pipe. So, minus del H1. So, that is equivalent to nothing but 3.3 minus 1.98, that is equal to 1.32 meter. Okay, let me clear this part, that delta H1 is basically the head loss due to the sand, due to the mixture of sand or due to the clogging of sand, while delta H2 is due to the clogging of sand, silts and clays. So, along the entire length of the pipe there will be two head losses, one due to the mixture of sand only, that is delta H1, and another due to the mixture of sand, silts and clays, that is delta H2. Now, the head loss will be along the entire length of the pipe, L1 for delta H1 and L2 for delta H2, because the pipe basically is of length of 1.5 plus 0.5 meter at the end. So, basically along this length the head loss will be only due to only due to the mixture of sand that is present here, while head loss at this point will be due to the mixture of clays that is present here, the sand, silts and clays that is present here. So, that is what we have done, delta H1 and delta H2, and then we have arrived at the conclusion that the head loss at the junction of the two plugs, that is basically at the point C or at this point, is HA minus delta H1, because the plug at the point, because the second plug is still absent here. At the end it is due to the second plug and the first plug, while at the point C it is only due to the first plug. So, that is what we have found out, 1.32. So, basically now we have the head loss at the point C is basically just 1.32 meter, because it is just above the datum, and so basically there is no, the Hz basically equivalent to 0 at the point C. So, now let us find out that how the distribution of the pressure diagram looks like. Now, at A we know the head loss is equivalent to 3.3 meter, and we are starting from this point. So, the distance is 0 meter. At C we know the head loss is 1.32 meter, this is at a distance of 1.5 meter. Is a distance of 1.5 meter at this point. So, this is 1.5 meter from the point A, while at B the head loss is 0 meter, and this is at a distance of 2 meter, that is 1.5 plus 0.5 meter. So, this is a distance of 2 meter. So, the point A will be here the point C will be here and the point B will be here. So, this distance is basically equivalent to 1.5, this is 2 meter, this is 0 meter. This is the distance in meter, this is the head loss. And this height is 3.3 meter, this is 1.32 meter and this is 0 meter, 0 meter. So, this is how the plot looks like, the plot of head loss versus, that is what we are asked, plot the variation of pressure, elevation head and total head over the entire length of the pipe. Now, this is the plot of the elevation head, pressure head and the total head over the entire length of the pipe, but actually this is the plot of the total head. Now, as we have said that the elevation head is 0, because you can easily see that the entire pipe lies along the datum. So, basically the elevation head, whether it is A, whether it is B, whether it is C, the elevation head is everywhere is 0. But the elevation head is actually 0. So, it is just a plot of the pressure head and the total head. This is a plot of just the pressure head and total head. The elevation head is 0, again I am telling the elevation head is 0 because the pipe lies along the datum. So, basically there is no elevation head in this point, there is only pressure head and there is a total head. As you have seen that basically here also when I said about the pressure at the point A, then also I told that basically the elevation head is 0, at B the pressure head is 0 and the elevation head is also 0, while at the point C the elevation head is 0 while the pressure head is 1.32 meter. So, that is how we have plotted the variation of pressure head and the total head against the length of the pipe along the distance. The second question is asked is that calculate the pore water pressure at the center of sand plug and the center of mixture of sands, silts and clays. Now, you have found out that what is the pressure heads at each of these points and the total head at each of these points. Now, from there we are going to find out what is the variation of the pore water pressure. So, how we are going to find out the variation of the pore water pressure? So, let us say that let us consider a point D first. Now, D is basically at the center of point A and point C, that means it is at the center of this sand plug or the center of this point. Okay, so, this is the point D. So, since it is the center of the point, since D is just at the center and since the variation from A to C is actually linear in nature, so we can find out the head D easily by taking a mean of the heads at point A and point C. That means the head at D, which basically is the center of sand plug, will be equivalent to HA plus HC by 2, because the variation from A to C is linear in nature as we have seen. So, this will be equivalent to 3.3 plus 1.32 by 2, this is equivalent to 2.31 meter. So, if you find out the head at D, then the finding out the pore pressure at D is very easy. So, 2.31 meter into the unit weight of water. So, this is equivalent to 2.31 meter into 9.807 kilonewton per meter cube. So, it is equivalent to 22.6 kPa. So, we have found out that what is the pore water pressure at the center of the sand plug. Similarly, the pore water pressure at the center of the mixture of sand, silts and clays, and also we found out because the variation from C to D is again linear in nature. So, the variation of the pore pressure at the center of the mixture of the center of sand, silts and clays will be equivalent to HC plus HD by 2, HB plus HC by 2, because again from the variation from C to B is linear in nature. So, let us consider another point E, which basically is the center of mixture of sands, silts and clays. So, this will equivalent to H B plus H C by 2. Now, H B we all know is 0 and H C is 1.32. So, divide by 2 into 0.66 meter. So, the pore pressure at this point will equal to 0.66 into gamma W, which is the unit weight of water. So, 0.66 into 9.807, you can even take 10 kilonewton per meter cube. So, this is equivalent to 6.5 kPa. So, we have found out the pore water pressure at the center of the sand mixture and the center of the sand, silts and clays mixture. Now, it was easy to find out, it was easy to find out because the variation is linear in nature. If the variation is non-linear in nature, then basically you have to find out the pressure head and data at every point. And as I have already said that the velocity head is always 0 because the velocity of water through sands through soils is very less. So, basically you only consider the pressure head and the datum head. Now, since you consider only the pressure head and datum head, there is an important point to note here. The sum of pressure head and datum head is known together as the piezometric head. And this piezometric head is very important because mostly in earth structures, when basically you are supposed to find out the phreatic line, which we will discuss in the next lecture. In that case, basically this piezometric head is very important because this piezometric head gives the idea about where the what is the pressure, what is the sum of the pressure head and the datum head at a particular point in the embankment. So, that basically you can find out that where is the location of the water table. It is very important because in most of the cases in embankments you have to find out the seepage loss or basically the flow nets and all those things. So, basically in all those cases, in order to find out the pore water pressures, you take help of this piezometric head. You just insert a piezometer at any point in the embankment and basically you find out the head loss at that point. Now, in the last question it is asked that what is the average hydraulic gradient in the sand and mixture of sands, silt and clays. Now, the average hydraulic gradient is very easy because we have already found out what is delta H1 and you also know what is the length along which the head loss is occurring. As I have said that in Darcy's law that H1 by L1 actually refers to the part that basically that head H1 is actually the head loss over the entire length L1. So, similarly here the head loss delta H1 due to the clog of sand we have found out to be 1.98 meter. So, this is 1.98 and the length over which the head loss is occurring is 1.5 meter. So, 1.98 by 1.5. So, this comes out to be 1.32. So, this is the average head loss in average hydraulic gradient in sand. And for the mixture of sand, silt and clay, similarly delta H1 by L2, this L2, delta H2 by L2, where L2 is 0.5 meter, that is the length of the mixture of silts and clays and sands. So, this is by 0.5 and delta H2 as I found out previously is 1.32 meter. So, this will be 1.32. So, this comes out to be 2.64. So, we find out that the average hydraulic gradient in case of mixture of sand, silt and clays is more than basically the mixture of sand, and this is obvious from the this plot of pressure head versus the distance, because we see that it is steeper in the case of sand, silts and clays while it is less steep in case of sands. So, we have discussed generally that how to find out a piezometric head in case if basically any question is given, that basically how to find out the piezometric head at a certain point, how to use the equation of continuity in order to find out the piezometric heads at certain points, and how it is useful in case of soil mechanics. Now, let us move to the next part, where basically I am going to discuss one important factor of this permeability and of this permeability fact, that how to use the effect of sand boilings, and basically mostly that how to find out the effect of sand boiling on the depth of excavations. So, basically we will consider a problem that a large size excavation is made in stiff clay. Saturated density is 1.76. When the depth of the excavation reaches 7.5 meter, cracks appear and water begins to flow upward to bring up sand to the surface. Subsequent borings indicate that clay is underlain by sand at a depth of 11 meter below the original ground surface. So, it is asked to find out that what is the depth to the water table outside the excavation below the original ground level. Now, here also first before we start doing the problem, let us discuss first thing how making excavation of clay affects the entire soil profile. Now, when you make an excavation of a clay, then this creates a hydraulic gradient. From the top of the sand layer to the bottom of the excavation, because if you see the diagram, means how basically it was made, then in this case let us say that this excavation that is made, and this is the sand layer. So, this is the clay, this is the excavation, and this is the water table. So, you see channel has been made from the water table to the sand layer. So, therefore, basically hydraulic gradient established between the sand layer and the top water layer. So, it creates a hydraulic gradient from the top of sand layer and bottom of excavation. That is what I said, that between this water layer, the water layer here, and basically the sand layer at the top. So, there is a hydraulic gradient between these 2 points. Now, what will happen as a consequence? So, as a consequence, water will now start flowing in vertical upward direction. And because clay has a very less permeability, so this flow equilibrium will reach after a long time. Now, the problem should be addressed only for a short time interval, and in this case we will consider two phases. The first is basically clay fissuration, because we have already said that that when basically the excavation is made, then cracks are appearing in the clay layer, that we have already said, cracks appear. So, now we have to first consider physically that when the floor of the excavation is going to be stable. Now, the floor of the excavation is going to be stable only if the water pressure P at top of sand layer that means at this point P, if P is the water pressure, is equivalent to weight of clay above it. Disregarding the shear strength of clay. So, now this equivalency condition means basically until and unless this equivalency condition is held, the clay is not stable. If the water pressure at the point P at the top of the sand layer is more, then basically what will happen is that the water will rush outside. So, in order to achieve this, what you have to say is that gamma total into H minus F. Now, what is this H and F? And what is this F? This F is basically from the top to this line. So, H minus F is actually equivalent to this length. H is basically the depth of excavation plus from depth of excavation, just the depth of excavation, because we do not want to consider any water table. So, basically F is just the depth of the excavation. So, H minus F. Now, the depth of excavation is said to be 7.5 meter. So, basically F is given as 7.5 meter and the value of H is given as 11 meter, because it is said the subsequent points indicate that the clay is underlain by sand at a depth of 11 meter below the original ground surface. So, basically the H is 11 meter. H is the length of the clay layer from the top of the ground surface. So, H minus F is just the thickness of this, or basically it is just the length where basically the hydraulic gradient is created from the top of the sand layer to the bottom of excavation. Now, so H we have found out that the length of the H is the height. H basically says the depth of the clay layer, while the F is the depth of the excavation. So, H minus F is nothing but the hydraulic gradient from the top of the sand layer to the bottom of the excavation. Now, gamma total is basically the total unit weight of the clay during that layer. So, in that layer. So, basically gamma total is nothing but gamma dash, that is the buoyant unit weight, plus gamma W, because we all know that gamma dash is nothing but gamma total minus gamma W, or gamma total can also be referred to as gamma bulk minus gamma W, or you can also refer to that as gamma sat minus gamma W if it is entirely saturated, if soil is saturated. So, gamma dash plus gamma W into H minus F. So, this is the water pressure P at the top of the sand layer. This is the water pressure. Now, to find out the water pressure P at the top of the sand layer. Now, this is the weight of the clay above the sand layer, because as you can see that this is the total weight of the clay of the sand layer. Now, what is the water pressure P at the top of the sand layer? That is very easy. That is equal to gamma W into H minus D. Now, what is this D? D is basically the depth of the water table from the top of the clay layer. So, D is depth of water table from top of clay layer. So, this is the pressure at that point. This is the pressure at this point. So, this length pressure is gamma W into H minus D, where D is this length and H is the total height of the clay layer that I have already said. So, in order to achieve the equilibrium condition, gamma W into H minus D must be less than the total weight of the clay layer, that is gamma dash plus gamma W into H minus F. So, if you solve this, then it comes out to be gamma dash into H minus F must be greater than gamma W into H minus D minus gamma W into H minus F. So, this equivalent to gamma W into H minus D minus H plus F. So, this is equivalent to gamma W into F minus D. So, gamma dash into H minus F must be greater than gamma W into F minus D. So, when failure will occur, if basically gamma dash into H minus F will be equivalent to gamma W into F minus D. So, then from here we can find out that gamma dash by gamma W is actually equivalent to F minus D by H minus F, or D is actually equivalent to F into gamma W minus H minus F into gamma dash by gamma W. We can again say that again let me repeat that what I have done, that during this clay fissuration, the first and important portion is that basically you have to consider that when that boiling condition is not going to occur. The boiling condition is not going to occur only if, disregarding the shear strength, only if the water pressure at the top of the sand layer is equivalent to the weight of the clay above it. So, we have found out that what is the weight of the clay above it. We considered that the height H is basically the height of the total clay layer, D is the depth of the excavation, and F is the depth of the excavation, and D, small d, is basically the height of the water table from the top of the clay layer. So, regarding that, we have found out the weight of the clay just above the layer of the sand and just below the excavation, which is equivalent to nothing but gamma dash, gamma, or basically you can say gamma sat into H minus F, because it is just under the water table. So, it took gamma sat. Now, gamma sat we can write it in the form of gamma dash plus gamma W into H minus F, while the weight water pressure at the top of the sand layer is taken to be as gamma W into H minus D, where D, as we have said, is nothing but the weight of the distance of the water table from the top of the clay layer. Now, in order to for the entire thing to be stable, or the excavation to be stable, basically we will consider that gamma W into H minus D, or the water pressure from the top, must be less than the weight of the clay layer above. So, that is what we have considered, and we have come to the conclusion that only failure conditions will occur if D is equal to F into gamma W minus H minus F into gamma dash by gamma W. Now, all these units are given, if you can see in the question, that basically the unit weight of clay, if the saturated density is given to be 1.76 and F is given to be F, or basically the depth of the excavation is given to be 7.5 meter, while the height of the clay layer is given to be as 11 meter. So, if you put all this, then you get D is equal to 7.50 into 1 minus 11 minus 7.5 into 0.76, which is equivalent to 4.84 meters. Now, in the second phase, we are going to consider the quicksand condition. Now, in quicksand condition, you have to first consider that what is the, you have to first consider the heads of the water at different points. So, basically we will draw this diagram again and we will find out that what are the heads at the different points. So, let us consider the head at this point is A, at this point it is B. So, what is the head at the point A? Now, as I have said, that is the piezometric head. Just in the previous question, we have said that is just the piezometric head. So, it is just the sum of the pressure head and the datum head, nothing else. So, if you consider the pressure head, that is nothing but UA by gamma W plus ZA. Now, of course, the ZA is 0. So, basically we will consider this as, of course, the ZA at this point at the A, we will consider this as H minus D, because D is the depth of the water table from the top of the clay layer and H is the entire length of the clay layer. So, H minus D into gamma W is the pressure at this point, obviously this is divided by gamma W, and ZA is 0 because this is the datum. So, this is equivalent to H minus D. Similarly, the head at point B will be equivalent to UB by gamma W plus ZB. Now, as we have known that the depth of the excavation is F, so this will be equivalent to H minus F into gamma W by gamma W plus 0 equivalent to H minus F, the pressure at the point D. Now, so the hydraulic gradient, so basically the hydraulic gradient is constant. Now, the hydraulic gradient is constant from A to B, because as you can see that this is just a water table, so it is linear in nature. So, basically the hydraulic gradient will be constant from A to B, and this can be given as HA minus HB, that is the head loss, divided by AB is equal to nothing but equivalent to I by is equal to I, which is equivalent to H by L. So, this will be equivalent to H minus T minus H minus F divided by L. L means this entire length. So, it is nothing but H minus F, this entire length of the this entire length. So, basically this is H minus F. So, this is D F minus D by H minus F. Now, considering critical conditions, if you consider I critical gamma dash by gamma W, then this head loss will be equivalent to gamma minus gamma W, that is gamma sat minus gamma W by gamma W. So, if we put those values, then we will get 7.5 minus D by 11 minus 7.5 will be equivalent to 1, because under critical conditions I gamma dash will be equivalent to gamma W, that we have already said, because that is what I said, water pressure at the top of the sand layer must be equal to the weight of the clay. That means that is what is the critical condition is, that is gamma dash, the water pressure at the top must be equivalent to the weight of the submerged weight of the clay if the height is same. So, that means gamma dash into H must be equal to gamma W into H. So, basically then gamma dash by gamma W will be equivalent to 1, then only critical conditions will reach. So, from here we found out that D is equivalent to 7.5 minus 3.5 equivalent to 4 meter. So, considering the weight of the clay, considering the clay fissuration, we have considered one aspect, and considering the quicksand condition, we have considered another aspect. Now, considering both the aspects, we find out that we will take the list height. So, basically 4 meter is the actual appropriate answer. Now, there are certain things that you have to remember in this case. The results will be same if basically the unit weight of clay and sand are equal. And remember that I have said, as just in the first case, that the shear strength, this is all disregarding the shear strength of clay. In the clay fissuration aspect, this is disregarding the shear strength of clay. So, basically the shear strength of clay is basically when you consider the first condition, then it was basically disregarding the shear strength of clay. In the second phase, the shear strength was also neglected, and also it was said in the second case the shear strength was also neglected. It was said that basically the water would rise to the cracks, because that is what the question was given as. Now, the shear strength of clay you can neglect if basically the width of the excavation is, if the width of the excavation in real life problems actually, if the width of the excavation is large enough, you can neglect the shear strength of clay, then basically it acts as a uniform load layer. Okay. But if the width of the excavation is small enough compared to the thickness of the clay layer, this is less than thickness of clay layer, then you have to consider the shear strength of clay. In that respect, you have to consider both the critical conditions as well as the shear strength of the clay layer. So basically today we discussed about the aspects of the quicksand conditions and basically about how you can find out the factor of safety against an excavation and basically how you find out the critical depth for an excavation. We also considered that what is concerned by the piezometric head and how do you find out the head losses at the different lengths along the pipe. In the next tutorial session that we are going to cover, we are going to consider about the embankments and how you are going to employ both this excavation, both these quicksand conditions, the effect of effective stress and the piezometric heads at different points in the clay layer, at different points for an embankment, and basically how to find out the phreatic line for an embankment using the parabolic theory that is already discussed in the lectures. Thank you.